Hello everybody and welcome back to another intoxicating quant interview video. This time around we'll be looking at random walks in 2 and 3 dimensions in a little problem I like to call a drunkard in search for home. So consider the following. A drunk man is standing at the origin of a 2-dimensional plane. At each point in time he has a 50-50 chance of moving 1 unit along the positive or negative direction of the x-axis. At the same time, he has a 50-50 chance of moving 1 unit along the positive or negative direction of the y-axis. Assuming he staggers around like this indefinitely, what is the chance that he will return to the origin? Furthermore, what about the case of a drunk bird moving around in 3-dimensional space? That is, what if we further introduce a 50-50 chance of moving 1 unit along the positive or negative direction of the z-axis? For those of you who decry this problem as hopelessly contrived and unrealistic, observe that birds getting hammered on fermented berries is in fact a naturally occurring phenomenon. So let's wet our beaks and get started with some random walk mathematics. Here we go. We'll start with the 2D case. The displacement along the x-axis can be +1 with probability of a half and -1 also with probability of a half. Meanwhile, the displacement along the y-axis can be +1 probability of a half, -1 probability of a half. To fully appreciate the implications of this, let's consider a graphical representation after just 1 or 2 time steps, to which end we need an xy coordinate system, which is what I'm sketching here. Now with probability 1/2, the drunkard takes a step in the positive x direction. With probability 1/2, he takes a step in the positive y direction, meaning that with probability 1/4, after the first step, he will find himself at coordinate 1.1. In a similar vein, if delta x is +1 and delta y is -1, then with probability 1/4, the drunkard will be at 1.-1. Analogously, he can be at -1.-1 with probability 1/4 and -1.1 with probability 1/4. Evidently, after the first time step, the probability of the drunkard having returned to the origin is 0. However, let's now consider what happens on the second iteration. Using a similar analysis with the 4 different starting points, we find that there's a totality of 9 different destinations of the drunkard after just 2 time steps. Interestingly, one of those destinations happens to be the origin point. Thus, after 2 time steps, the probability that the drunkard finds himself back at the origin is given by the 4 cycles, each of which have probability 1/4 into 1/4, which is just 1/16. We have 4 of them altogether, so the probability that the drunkard is back at the origin is given by 4/16, which is 1/4. Great, so let's start out by defining P as a probability of the drunkard returning to his origin point. Furthermore, define E of R as the expected number of returns to the origin. The strategy which we are here pursuing is to compute the expected number of returns and couple that directly with the probability of returning to the origin. To this end, know that p to the power of j, 1 minus p, is a probability of making exactly j returns to the origin. That is of course just the geometric distribution. Thus, E of R is going to be given by the sum from j equals 0 up to infinity of j multiplied by the probability of exactly j returns. To compute the sum, we'll use a neat little trick wherein we differentiate p to the power of j with respect to p. Taking the constants and the derivative outside of the sum, we are left with a sum over p to the power of j, which is of course nothing but a geometric progression. Using the result for infinite geometric series, that's just 1 minus p into p ddp of 1 divided by 1 minus p. Differentiating, that's 1 minus p into p, 1 divided by 1 minus p squared, which simplifies to p divided by 1 minus p, assuming that p is less than 1. So in summary, when p is 1, then the expected number of returns to the origin is going to be infinite, and when p is less than 1, then the expected number of returns is going to be finite. Now define the random variable r sub n as 1, just in case that the drunkard happens to be back after n steps, and 0 otherwise. Furthermore, let's define p sub n as a probability of being back after n steps. Then we have that the expected value of Rn is 1 into p sub n plus 0 into 1 minus p sub n, which is of course just p sub n. Now define R as the sum from n equals 1 up to infinity of R sub n. That is to say, R effectively counts the number of returns to the origin. Then we have that the expected value of R is going to be the sum ranging from n equals 1 to infinity of E R sub n, which is again the sum from n equals 1 to infinity of P sub n. Now notice that the probability of being back after an odd number of steps is 0, since each outbound step must be matched by an equal and opposite return step. So P sub n is 0 if n equals odd. So the expected value of R should really be written as a sum over all even-numbered probabilities, where P sub 2n in turn can be decomposed into the probability of x being equal to 0 after 2n steps, multiplied by the probability that y equals 0 after 2n steps, since steps in the x and y direction are independent. So let's work out these probabilities. For x, we have that after 2n moves to return to the origin, half of them must be in the positive direction, half of them must be in the negative direction. And there's going to be a totality of 2n choose n such series, each of which is going to have probability of a half raised to the power of 2n. And of course the exact same thing applies to y. Great. So the probability p sub 2n is simply going to be 2n choose n, a half raised to the power of 2n, this expression squared, and using the definition, that's just 2n factorial, n factorial, n factorial, a half raised to the power of 2n squared. To proceed, we will invoke Stirling's formula, which asserts that for large n, n factorial may be approximated as the square root of 2 pi n multiplied by n over Euler's constant raised to the power of n. So for large n, p2 sub n may be approximated as square root of 4 pi n into 2n divided by e raised to the power of 2n, this divided by 2 pi n into n over e raised to the power of 2n into 2 to the power of 2n, this squared. This simplifies to 1 over root pi n squared, which is nothing but 1 over pi n. With this in mind, the expected number of returns to the origin is given by the sum from n equals 1 to infinity of p sub 2n. This in turn can be approximated by the sum from n equals 1 to infinity of 1 over pi n. Taking the constant pi out, that's just the sum from n equals 1 to infinity of 1 over n. Well, lo and behold, this is of course nothing but the old well-known harmonic series, and it is well known to diverge. In other words, E of R is infinity, and we conclude that the probability of returning to the origin for the drunkard is unity. So this answers the first part of the question. All drunkards, except a measure 0 of them, will eventually stagger their way back to the origin. Now let's consider the three-dimensional case, that is to say delta x equals +1 and -1, each with probability of a half, delta y equals +1 and -1, each with probability of a half, and finally delta z is +1 and -1, each with probability of a half. Let's visualize the first time step in a three-dimensional coordinate system. So imagine that we have a cube which is centered around the origin. Then for the first time step, the drunken bird will shoot out into any of the 8 corners of the cube, and this will happen with probability 1/8 for each of them. So very briefly, let's label the 8 coordinates that can materialize after this first time step. So by analogous computations, p sub 2n is going to be the probability of x equals 0 after 2n steps, multiplied by the probability that y equals 0 after 2n steps, multiplied by the probability that z equals 0 after 2n steps. And this we already know, it's going to be 2n, choose n, multiplied by a half, raised to the power of 2n, this expression cubed. So by the Stirling approximation, that's just 1/πn raised to the power of 3/2. Now the expected number of returns is simply going to be the sum from n equals 1 up to infinity of 1/πn raised to the power of 3/2. And by the integral comparison test, that's going to be the integral from 1 to infinity of dn over πn 3/2. And we can evaluate that to 1/π 3/2, and then n to the power of -1/2 divided by -1/2, this expression between 1 and infinity, which is of course just 2/π 3/2, which is of course less than infinity. Given that E of r is finite, we deduce that the probability that the drunk bird returns to its origin is less than 1. The exact value for p requires either much patience or the use of a computer, but you should find that the answer is somewhere in the ballpark of 30%. Summarizing what we've learned today, I can think of no finer quote than that of Shishu Kakutani, the Japanese-American mathematician who famously said that the drunk man will find his way home, but the drunk bird may get lost forever. Well, I'll let you continue your random walk through YouTube, but I do hope to see you back again for another Quant interview video. Bye bye.